Hi guys. So today I want to start talking about continuous time models. And before we do that, let's review a little bit of probability theory. So the first thing I would like to talk about is infinite probability space. Now, infinite probability space is used to model a situation where an experiment has infinitely many possible outcomes. Okay, so if we consider an experiment of drawing a number between 0 and 1, there are infinite many numbers between 0 and 1. Okay. Likewise, if you basically consider another experiment where we take a coin and we toss it infinitely many times, the number of possible outcomes there as well is infinite. Okay. So in the first experiment, let's denote the sample space by capital omega, and this would be set of all numbers between 0 and 1. Okay. In the second experiment, where we take a coin and toss it infinitely many times, we're going to denote the sample space by capital omega of infinity, and this is just going to be set of all outcomes that we get by tossing a coin infinitely many times. Okay, coin toss infinite many times. Okay, now these two infinite sample spaces are not just infinite, they are uncountably infinite. Okay, they are uncountably infinite. Now, what do we mean by uncountably infinite? Well, by uncountably infinite, we mean that their elements cannot be arranged in a sequence. Okay, so for example, if we take two numbers here, 0.000000111, 0.000000112, we can't still arrange them in a sequence because in between these two numbers also there are going to be infinitely many more numbers, right? And in between any two numbers, basically there are going to be infinitely many numbers. Hence, we cannot arrange them in a sequence. So the first problem that we have is with uncountably infinite sample space is that probability of a particular outcome is 0. So if we denote the any particular generic outcome in these experiments by omega, okay, then probability of a particular outcome is 0. Okay, that basically happens in an uncountably infinite sample space. So now if we have an event A and we want to figure out what is the probability of an event, we can't sum probabilities of all omegas where omega belongs to A. So if you remember when we were talking about finite probability space, when we were discussing binomial model, if you wanted to calculate probability of an event, this is exactly what we did. Okay, but here, because probability of a particular outcome is 0, we can't really sum across probabilities like that. So what we need to do then in an uncountably infinite sample spaces, we need to actually specify the probabilities of events directly. Okay, but in an uncountably infinite sample space, there are uncountably infinite, or there are infinite number of events. So it's going to be hopeless to actually specify probabilities of each one of those events, right? Because there are just infinitely many. So what we're going to do is we're going to actually specify probabilities for simple sets, okay, and then we're going to use properties of probability measure to get probabilities for complex sets. Okay, so this is the approach we're going to take. Since there are infinitely many subsets or many events, we cannot really specify probabilities directly for each one of those sets because they're just infinitely many. So what we're going to do is we're going to take this approach. We're going to specify probabilities for certain simple sets, and then we're going to appeal on the properties of probability measure to get probabilities on more complicated sets. Okay, so that basically is the way we're going to actually approach this problem. So just to recap again, we basically want to discuss infinite probability space because we are considering two experiments where the possible number of outcomes is basically infinite. Okay, now it's not just infinite, they are uncountably infinite. That means that we cannot put the outcomes in a particular sequence. Okay, and the problem we have with uncountably infinite sample space is that probability of any particular event or any particular outcome, is going to be equal to 0. Hence, we cannot use this formula to calculate the probability of a particular event. So what we need to do is, we need to specify probabilities of these events directly. But since there are infinitely many events, it's not easy for us to basically specify probabilities directly for each particular event there. So what we're going to do is, we're going to use this approach. We're going to specify probabilities of certain simple sets, okay, and then we're going to use the properties of probability measure to get probabilities on more complicated sets. Okay, so that basically is our approach. And what I would like to discuss now is some of the machinery that we're going to use in order to do this. And the first thing we're going to discuss is sigma algebra. Okay guys, so what I want to do now is I want to discuss sigma algebra. So let's consider a non-empty sample space given by capital omega. And let's also have a collection of subsets of the sample space which is given by f. Okay. Now this collection of subsets is basically called a sigma algebra if the following are true. That empty set belongs to sigma algebra. Okay, this is the first condition. Second, if a set belongs to sigma algebra, then its complement also belongs to sigma algebra. Okay. Third, if a series of sets belong to sigma algebra, then union also belongs to sigma algebra. So it's an infinite union that also belongs to sigma algebra. So again, what do we have? We basically have a non-empty sample space. F is basically a collection of subsets of the sample space. And this F is basically a sigma algebra if these three are true. So an empty set belongs to sigma algebra. If a set belongs to sigma algebra, then its complement also belongs to sigma algebra. And if a series of sets belong to sigma algebra, then its union I equals 1 to infinity also belongs to sigma algebra. Okay? So a couple of things actually we can see from here, that if we have, let's assume that we have two sets A and B. From this, we can see that A union B also belongs to sigma algebra. And how we can actually see that? Well, A1 we can substitute for A, A2 can be B, A3 onwards we'll basically give it an empty set. Okay? So according to property 3 then, A union B union all empty sets till infinity would give us A union B, and this according to this property, this also belongs to sigma algebra. Okay? Likewise, if we have a finite number of sets A1, A2 all the way to AN, from this property we can see that union of these finite number of sets also is part of sigma algebra. Why? Because AN plus 1 till infinity we can take them to be empty sets, and from here then we can see that the union would be part of the sigma algebra. Okay? Now one other interesting thing is that if we basically consider intersection of these sets, so if for example we have I equals 1 to infinity A of I, so we basically are taking intersection of all of these sets. Since the intersection can be written as a union, so we can write intersection as union of AI complement, okay, and complement of this. Then this intersection also belongs to sigma algebra. And why is that? Because see, according to property 2, if a set AI belongs to sigma algebra, then its complement also belongs to sigma algebra. So all of these complements belong to sigma algebra. If these complements belong to sigma algebra, then according to property 3, the union also belongs to sigma algebra. Okay, so this quantity inside the bracket actually belongs to sigma algebra. And if this belongs to sigma algebra, according to property 2 again, its complement belongs to sigma algebra. So the intersection also, the infinite intersection also belongs to sigma algebra, and according to the same logic that we just talked about here, where I showed you a finite number of sets, their union belongs to sigma algebra, we can easily show that the finite intersection also belongs to sigma algebra. Okay, very simple. What we need to do is beyond n we need to consider all the other sets as empty set, and then this would basically give us this property. Okay, so this basically is what is a sigma algebra. So basically, again, we basically have a sigma, we have a non-empty sample space, and we have a, you know, a collection of subsets, and a collection of subsets given denoted by f is called a sigma algebra if these three properties are true. And a result of these three properties is a finite number of sets, basically a union of them, is also in sigma algebra. Since intersection of sets can be written as union of sets like this, I've shown you that this also belongs to sigma algebra, and from here a finite intersection also belongs to sigma algebra. Okay, now what is the easiest sigma algebra we can construct? Well, think about, we basically put only the empty set as part of our sigma algebra, and let's go through these properties now. So empty set belongs to sigma algebra. Okay, so we basically put an empty set in our sigma algebra. If this belongs to sigma algebra, then its complement also belongs to sigma algebra. So its complement is basically the entire sample space. So let's put that in the sigma algebra. So this basically is the simplest sigma algebra that we can create, and it satisfies all these properties, right? So empty set belongs to sigma algebra, which is true here. Its complement belongs to sigma algebra, which is also true. And the union, if we basically take a union, that basically would be the entire sample space again, that also belongs to sigma algebra. So this is the simplest case of a sigma algebra. So what we're going to do is, we can basically, in order to construct a sigma algebra, then we can start with certain sets. Okay, it can be any sets, and then we can basically use these properties to fill other sets, so that we basically make a sigma algebra. Okay, so like we started with a null set, and we basically put the entire sample space to make it a sigma algebra. Likewise, we can have some other sets here. Okay, and then we can put all the complements of those sets within the sigma algebra. Then we can put all the union within the sigma algebra, and that's how we can construct a sigma algebra. Okay guys, so hopefully sigma algebra was clear. Now let's move on to probability measure. Okay guys, so now I want to talk about probability measure. So let's consider we have a sample space given by capital omega, and we have a sigma algebra given by capital F. A probability measure is a function that assigns to each set that belongs in the sigma algebra a number between 0 and 1. Okay, it will give a number between 0 and 1 for all sets that belong to our sigma algebra. Okay, that basically is what a probability measure is. Now, what are the properties of this probability measure? The probability of the entire sample space is equal to 1, 2, and if we have a series of disjoint sets like A1, A2, A3, blah blah blah, probability of union of I equals 1 to infinity of AI is equal to summation of I equals 1 to infinity probability of AI. Okay, where AI are, all these sets are disjoint sets. Okay, now from here we can come up with some interesting conclusions. What are the probability of the empty set? Well, if we substitute all AIs as empty set and we use property number 2, what do we get? So this will become probability of union of AIs, and all of these sets are empty sets, so this becomes just an empty set. Union of all empty set becomes the empty set. This is equal to summation of I equals 1 to infinity of P of AI, because AI is phi. Now, since P is a number between 0 and 1, the only number that can satisfy this equation is if P of phi is equal to 0. Okay, so we get P of phi equals to, or the empty set equals to 0. So that's one conclusion. Then the second thing we can basically see is, now the sample space I can write as union of a set A and its complement, right? That basically, a union of A and its complement basically gives it the entire sample space. This is equal to 1. So now because these A and its A complement are disjoint sets, I can write this as probability of A plus probability of equals 1, or P of A equals 1 minus P of, right? So this basically is another conclusion that we get. Now this is an infinite union, but if we have a finite union, so if we have two sets A and B which are disjoint, okay, then probability of A union B is equal to probability of A plus probability of B. This basically comes from this property right here. What we can consider is the first set to be A, second set to be B, third set onwards till infinity we're going to take them as empty set. And if we plug those things here, we'll see that this basically holds true, right? And similarly, not just for two sets, this basically is true for finitely many sets. So probability of union of 1 to n of AI is equal to summation of I equal 1 to n probability of AI. So this basically is true for finitely many sets as well. Okay? So this basically completes my discussion on probability measure, and basically I showed you what probability measure is. Basically it's a function that assigns probability to each set in the sigma algebra and gives it a number 0 and between 0 and 1. Probability of the entire sample space equals 1, and if we have a series of disjoint sets, the infinite union, we can get probability as summation. And then I showed you probability of a empty set is 0, probability of a set is equal to 1 minus its complement. Then probability of two disjoint sets A and B is equal to probability of A plus probability of B. And probability of a series of a finite number of disjoint sets is summation of probabilities of individual sets. Okay? So this basically concludes my discussion on probability measure. Now this triplet, okay, this triplet of sample space, a sigma algebra, and a probability measure is basically called a probability space. Okay, so for a probability space we need a sample space, we need a sigma algebra, and we need a probability measure that operates on that sigma algebra. Okay. As far as I'm concerned, basically for me, the way I think about it is, sigma algebra is basically a collection of all those sets for which a probability measure is defined. Okay, that's another way to basically look at the same thing, right? Cool. So far we've talked about a sigma algebra, then I showed you what a probability measure is. And now what I would like to do is I would actually like to take our experiments, which basically we had two experiments, drawing a number between 0 and 1 and tossing a coin infinitely many times. And I would like to create a mathematical model for choosing an outcome from these experiments. Okay, so let's do that next. Okay, so let's consider our experiment of drawing a number between 0 and 1. Okay, I would like to define a probability measure on this such that probability of drawing a number between A and B is given by B minus A. So 0 is less than or equal to A, less than or equal to B, less than or equal to 1. Okay, now this probability measure is called the uniform probability measure, or the Lebesgue measure. Okay, so basically the probability of drawing a number between an interval A and B is just the length of the interval, okay, given by B minus A. From here we can easily see that probability of drawing a number A or drawing a number B is also is equal to 0. So for example, if you want to figure out what is the probability of drawing a number A, so I substitute B equals A, so this becomes AA, closed interval, A minus A, which is equal to 0. So probability of drawing a number So probability of drawing a number A is equal to 0. And hence we can actually write this closed interval as an open interval as well. Okay, we can write probability of open interval A and B is also equal to B minus A, because probability of getting either A or B is 0. Hence we can actually write this as an open interval. Now this probability measure basically gives us the probability of intervals. Okay, so for example, if I want to figure out what is the probability of drawing a number between 0 and 1 by 3, from this formula we know that it's going to be equal to 1 by 3. Okay, but what if we want to figure out probability of more complicated sets? For example, we could actually we could want to calculate the probability of drawing a number between 0 and 3 and union of 2 by 3 and 1. Okay, so looking at the formula itself is not going to give us the probability here, but if you look at the properties of probability measure, since these two sets are disjoint, we know that this basically is equal to probability of 0 1 by 3 plus probability of 2 by 3 1, right? And this is equal to 1 by 3 plus 1 by 3 equals 2 by 3. So even though this is not really an interval, but using this formula and the properties of the probability measure, we can figure out the probability. And we can do the same for many more complicated sets. So then it's natural to ask if there is a way to describe the collection of all sets whose probability is given by this particular formula and the properties of the probability measure. Okay, so basically now we're basically asking the question that can we figure out for which sets probabilities are defined using this formula and properties of probability measure. It turns out that the collection of sets for which the probability is defined is basically a sigma algebra that we get by starting with all closed intervals. Okay, so we basically put in that sigma algebra all the closed intervals between 0 and 1, and there are infinitely many closed intervals. We put all the closed intervals in that in the sigma algebra, and then we put all the other sets which are required to make it a sigma algebra. So if you remember properties of sigma algebra, we basically had said sigma algebra basically has, okay, so if a set belongs to sigma algebra, then its complement also belongs to sigma algebra, and if a series of sets belong to sigma algebra, then its union belongs to sigma algebra. Then I showed you that a finite union also is part of the sigma algebra, intersection is also part of the sigma algebra, and likewise, right? So in order to figure out all the sets for which the probability is defined, once we have this formula and the property of the probability measure, we start with all closed intervals, and then we put everything else which is required to make it a sigma algebra according to our properties of sigma algebra. Okay, once we do that, that collection of sets, basically we can figure out probabilities of all those sets under that sigma algebra. Okay, also note that since an open interval can be written as a union of a sequence of closed intervals, all open intervals are also part of the sigma algebra. Okay, so we have all closed intervals, all open intervals, unions, intersection, all of those stuff basically part of a sigma algebra, and for all of those sets the probability is defined. Okay, so now let me describe what do you mean by a Borel sigma algebra. Okay, so Borel sigma algebra is basically a sigma algebra that we start by taking closed intervals of, by taking all closed intervals of 0 and 1, and then adding everything else that's required to make it a sigma algebra. Okay, and that basically sigma algebra is called a Borel sigma algebra of subsets of 0 and 1, and we write it as Borel 0, 1. Okay. Now all the sets in this Borel sigma algebra are called Borel sets. Okay, they are called Borel sets. Now, all the sets that we're going to encounter in our discussion, basically, all the subsets of 0 and 1 that we're going to encounter in our discussion, they're all going to be Borel sets, for which we know that the probability is defined once we basically define the probability of the closed interval and we apply the properties of probability measure. Okay? So just to recap again, basically we defined a uniform probability measure here, which is just the length of the interval. Then we said that, okay, probability of each point is actually 0, hence this probability of a closed interval is the same as probability of an open interval. Then we said that, okay, this basically gives us the probability of an interval, but we can use the property of probability measure to figure out the probability of much more complicated sets. Okay, like one of the sets, this is not very complicated, but just for illustration, I've basically shown you that. Then we asked the question that, okay, can we specify a collection of all the sets for which the probability is defined once we define this formula and we know what the properties of probability measure are. And we said that, okay, if we basically construct a sigma algebra starting with closed intervals, all the closed intervals, and we put everything else that's required to make it a sigma algebra, then that collection basically is a universe for which the probability is defined by this particular formula. And if we start with, you know, all closed intervals of 0 and 1, and we put everything else that's required to make it a sigma algebra, then that particular sigma algebra is called a Borel Sigma algebra, or subset of 0 and 1, which is denoted by B of 0 and 1. Each set in that Borel Sigma algebra is called a Borel set, and for which we know that the property is determined once we specify the probability of the closed intervals. Okay, hopefully that discussion was clear, how we basically constructed a probability measure on 0 and 1. And then how we figured out a collection of all sets for which the probability was defined. And I said that collection of all the sets for which probability is defined is basically a Borel Sigma algebra denoted by B of 0, 1. Okay guys, next I would like to actually discuss our other experiments. So we basically already accounted for probability measure for our interval 0 and 1. Now we have another experiment going on where we toss a coin infinitely many times. So let's discuss that next. Okay, so now let's consider an experiment where we take a coin and we toss it infinitely many times. The sample space is given by capital omega of infinity. Let's consider that probability of tossing a head is given by P and probability of tossing a tail is given by Q. Okay, and I would like to actually specify a probability measure on this. Okay. So the way we're going to do it is, let's assume that we basically start with two sets, f of 0. F of 0 is basically a sigma algebra that consists of two sets, an empty set and the entire sample space. Okay. Now we know what the probabilities for these two sets are, right? So probability of an empty set we know for sure is 0. Probability of the entire sample space is equal to 1. Next, we're going to describe two sets, A of h and A of t. A of h would be all sequences that start with a head. So here we're going to put all sequences that start with the first coin toss as a head. Likewise, in A of t, we're going to put all sequences that start with a tail. Okay? And now we're going to describe another sigma algebra, f of 1, where we're going to put empty set, we're going to put the entire sample space, we're going to put A of h and A of t. Now if you remember from definition of sigma algebra, if you put a set in it, we need to also put its complement. Okay? But do understand that complement of a null set is basically an entire sample space, and complement of A of h would be A of t. So we already have the complements in our sigma algebra. We do not need to add anything else to the sigma algebra. Okay? So these four sets also constitute a sigma algebra. And we say f of 1 because here we basically are constructing a sigma algebra of those sets that can be described in terms of one coin toss. So here you will see we have defined two sets that can be described in terms of the first coin toss. Okay, first coin toss, it's a head. Basically, let's put all the sequences here. If first coin toss is a tail, let's put all the sequences here. Okay. So now if you want to figure out what is the probability of all of these sets, as we talked about, probability of a null set and the entire sample space is given right here. Now probability of A of H, what would this be? Well, here we're putting all sequences that start with a head. Okay. This should basically be, the probability of this set should be equal to P, because that's exactly how we've defined it. Probability of tossing a head is P, and here we are putting all sets where the first coin tosses a head. So this should actually be, probability should be equal to P. Likewise, probability of A of T should be equal to Q. Okay. So we've defined sigma algebra F1, and we know probability of all of these four sets. Now again, let's define another four sets: A of HH, A of head tail, A of tail head, A of tail tail. Here we're going to put all sequences that start with a head head, right? Here we're going to put all sequences that start with a head tail. Here we're going to put all sequences that start with a tail head. Here we're going to put all sequences that start with a tail tail. Now again, these four sets can be described in terms of the first two coin tosses. Okay, and let's describe a sigma algebra called F2, and here we're going to put phi. Here we're going to put the entire sample space. Then we're going to put A of HH, A of head tail, A of tail head, A of tail tail. Now once we put a particular set in there, we also need to put its complement, right? Complement of head head, A of head tail complement, A of tail head complement, A of tail tail complement. And now we need to put all unions. Okay, so what is the union of AHH? AHH union of A head tail is nothing but A of H. Okay, so let's put A of H in there. Likewise, A of tail head union A of tail tail is A of tail. So let's put A of tail also in there. Okay, now let's put all the other unions. So we're going to put A of head head union A of tail head, A of head head union A of tail tail, A of head tail union A of tail head, A of head tail union A of tail tail. Well, we also need to put all the triple unions, that union of any of these three sets. But remember that if we take triple union, A of head head union A of head tail union A of tail head, this is nothing but the complement of the fourth set. Okay, if we take union of any of these three sets, it would give us the complement of the fourth remaining set. And complements of all of these sets are already here. So triple unions are already part of our sigma algebra here. So we don't need to add anything else to our sigma algebra. Okay, so this would give us 16 sets. Okay, and let's figure out if we know how to calculate the probability of these 16 sets. We know the probability of this, probability of this. We know the probability of A of head and A of tail, right? Now A of head head would be, because these two coin tosses are independent, this would be P square. This would be PQ, probability of head times probability of tail. This would be PQ as well. This would be Q square, right? Complement would be 1 minus probability of A of head head, which is P square. So we know probability of all of these four also using our properties of probability measure. And since these four sets are they are separate from one another, we basically know disjoint sets they are. So we basically, these four sets are disjoint, so we can figure out the probability of these four sets also. This would be just probability of A of head head plus probability of A of tail head. Okay, and we know what these probabilities are. So we know probabilities of all sets under F2. Likewise, we can continue this process. We can basically create a sigma algebra F3. Here we're going to put all sets that can be described in terms of the first 3 coin tosses. Then we can put another sigma algebra F4. Here we're going to put all sets that can be described in terms of 4 coin tosses. And probabilities of all of these sets would be known according to the same approach that we're taking here. And we can continue this process till we basically reach f of infinity. And here we're going to put all sets that can be described in terms of finite number of coin tosses, and we're going to put everything else that's required to make it a sigma algebra. Okay, so what is f of infinity? It basically has all sets that can be described in terms of finite number of coin tosses, and we put everything else that basically required to make it a sigma algebra. Okay, some of the sets here cannot be described in terms of finite number of coin tosses. So for example, if you want to figure out the probability of head, head, head infinite sequence of this, okay, now this obviously cannot be described in terms of finite number of coin tosses because it basically is an infinite series of heads. Okay, but once we know what the probability of all finite all sets which can be described in terms of finite number of coin tosses, probability of this is also determined, and let me show you how. So probability of head we know was p, probability of head head we know to be p square, probability of head 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 we know to be p cube, likewise, right? And since p is basically a number between 0 and 1, these probabilities are converging to 0. So even though directly we don't know what the probability of the sequence is, we know through this that probability of infinite series of heads is equal to 0. Okay, so we can take the same approach to figure out probabilities of sets here that cannot be described in terms of finite number of coin tosses, and I claim that basically we can still determine the probabilities of those sets. Okay, now all the sets that we're going to encounter in our discussion of any subset of capital omega of infinity that we encountered in our discussion would be part of our sigma algebra f of infinity. Okay, it's actually very difficult to find a set which does not belong to this particular sigma algebra. Okay, so that basically is the discussion of how we're going to go about creating a probability measure for this particular sample space. Okay, so we basically have created different sigma algebras that can be defined in terms of finite number of coin tosses. Then we put all finite number of coin toss sets which can be described in terms of finite number of coin tosses, and put everything else, and using this approach we can figure out probabilities of all of those sets. Okay guys, so that's all I wanted to talk about today for this particular thing. Next we're going to talk about random variables and their distribution.